Good day, viewers. I welcome you to today's class on two-way Anova and the completely randomized block design. In our last class, we looked at the one-way Anova. Anova stands for analysis of variance. We looked at the one-way analysis of variance in our last class, and today we are looking at the two-way analysis of variance. In statistics, there is what we call design and analysis of experiments. Design and analysis of experiments. Some experiments are designed and we use the one-way Anova to solve such experiments. Such experiments have just one factor, a single factor, known as the treatment. And such a design is called the completely randomized design. The statistical models for the one-way Anova is given as this: mu plus alpha I plus EIJ. Mu stands for the population mean, alpha I stands for the effect due to treatment I, while the EIJ stands for the error term. Once again, I welcome you to class today. My name is Dr. Chris Isekaibe. I want to encourage you to wait patiently to the end of this video so that you can learn a lot about the two-way analysis of variance. My YouTube channel is Dr. Chris Isekaibe. That is my name. I am Dr. Chris Isekaibe. I am a chief lecturer and a member of the academic board of one of the most prestigious polytechnics here in Nigeria. I hold a doctorate degree in mathematics with distinction, a master's degree in mathematics, and a bachelor degree in statistics. I have written quite a number of books in statistics and in mathematics. My area of specialization is numerical analysis. I also specialize in data analysis and modeling, statistical analysis, and scientific computing. Why not, if you are an artificial intelligence firm, you deal on artificial intelligence, why not I can work with your team of mathematicians and statisticians to develop advanced mathematical statistical models or algorithm for artificial intelligence. Or if you are a research firm or institute across the globe, why not I will be, you can contact me to be part of what you are doing. I have scholarly publications in renowned publications in Nigeria and outside Nigeria, and I've also presented papers in renowned conferences within and outside Nigeria. I will be looking forward to hearing from you. You can contact me if you are a postgraduate student or undergraduate student or a research institute or an AI firm. You can consult me so that we can work together. I am a consultant in numerical analysis, data analysis, and modeling. I will be looking forward to hearing from you. Once again, my contacts are +234 8033 021 If you are calling from outside Nigeria, this first number is for call and WhatsApp. If you are calling from outside Nigeria, it is good you put this code +234. Then my second number is +234 7066 297535. This one is only for call, not for WhatsApp. The first one is for call and WhatsApp. Then my email is chrisdavid2015@gmail.com. I will be looking forward to hearing from you. So, without any delay, permit me to go into the business of the day. In our last video, we looked at the one-way analysis of variance, and the one-way analysis of variance is also known as the single factor Anova. It can be used to analyze only one factor with several groups, and the groups are assumed to have been drawn from a different population that are assumed to be normally distributed, and each population is expected to have the same variance or standard deviation, and the factor itself is categorical, but the responses are numerical. That makes it a parametric test. So the analysis of variance is a parametric test. It is, we use variances to study or to test for equality among means or averages. So today we are looking at the two-way Anova and the completely randomized block design. In our last class, we looked at the one-way Anova. Now, in statistics, there is a special topic called design and analysis of experiments. We make use of analysis of variance. The short form for analysis of variance is Anova. We make use of analysis of variance to design and analyze these experiments in various fields, in agriculture, in medicine, and so on and so forth, in different fields. So once again, my YouTube channel is Dr. Crbd. Please subscribe to my YouTube channel, share my videos in your social media platform, click on the like button, share them, share the videos across the world. The essence of this channel is to share knowledge, contribute my own quota in sharing knowledge across the globe. And as you do, God will bless you on every side. So this topic, design and analysis of experiment, is a very special topic in statistics. We have various tools for designing and analyzing this experiment. The first tool is the one-way Anova, or generally we use the analysis of variance. Analysis of variance makes use of variances to compare equality among means of population. So when it involves the test of hypotheses, the HO, the null hypothesis, will always tell you that the population means are equal. Then the alternative hypothesis, which contradicts or opposes or complements the null hypothesis, will always tell you that the population means are not equal. At least two of them are not the same. So the first one, the last video we treated, each of these tests have what we call statistical models. Now for the one-way Anova, analysis of variance, we use the one-way analysis of variance to analyze the completely randomized design. The completely randomized design has a single factor. So that's why we make use of the one-way Anova to analyze it and get results. So now, this is the model, the statistical model for the one-way analysis of variance. The one-way analysis of variance is used for the completely randomized design. Now, what this mu means, this mu in statistics, it means the population mean. Then this alpha I means the effect of the ith treatment. Then the EIJ means the error term. Now we are looking at this statistical model for the one-way. We treated one-way last week. Then this YIJ means the observations. The YIJ means the observations, or you can say the ith observation in J triplicate. You can call it the ith observation in J replicate. So that is what the YIJ is. Now, the difference between the one-way analysis of variance and the two-way analysis of variance is that the two-way analysis of variance takes care of an additional source of variation called the block. So the two-way analysis of variance is used to analyze the completely randomized block design. Completely randomized block design. Completely randomized block design. Block design. That is what the two-way analysis. So this, you can see both of them, the model for the one-way, the model for the two-way, they have the population mean. Then this one is the effect due to the ith treatment. then this is the error term. But this one has an additional source of variation where our beta j is the effect due to the jth block. The effect due to the jth block. So that is what the two-way analysis of variance does. And the source of variation, there is an additional source of variation called the block. Now, the completely randomized block design is perhaps the most commonly encountered design that can be used as a two-way Anova. It can be used as a two-way analysis of variance. In this design, the design of the randomized complete block design or the completely randomized block design, in this design, we set up an experiment or an experimental unit that is grouped. And this experimental unit that is grouped is called the blocks. The blocks are grouped in a way that it minimizes or they minimize the variability among the units within the various groups. Now, the objective of creating this additional source of variation called the block is to keep the experimental error within each block as much as possible. Each block will definitely contain the complete set of treatments. Therefore, the differences among blocks are not due to the treatment. So each block will now contain all the treatments. So you are not going to have another source of variation called the sum of square for blocks. So as a matter of fact, therefore, differences among blocks are not due to treatment. And this variability can be estimated as a separate source of variation. So we can now do that or estimate it as a separate source of variation. So the greater the variability among the blocks, the more efficient the design becomes. You know, for the one-way Anova, which is the same thing, which is used to analyze the completely randomized design, the error is large. The degrees of freedom for error is large. But now, when you are now introducing the block that will contain all the treatment, each block will contain all the treatment, the degrees of freedom for error will now be reduced. So, in the absence of any appreciable block, the randomized block design is not different. It's not more efficient as the completely randomized design. So it is very, very important for us to know that the completely randomized design has more degrees of freedom for error. That is the one-way Anova has more degrees of freedom for error. But when the blocks are introduced, the degrees of freedom for error for the completely randomized design, which is the one-way Anova, will now be reduced. And when the complete randomized design, when the degrees of freedom for error is large, it will result to a smaller F ratio. And that smaller F ratio will definitely be used for significant difference, to test for significant difference among the treatments. So it is important we have this and know how it works. So an additional source of variation is added for the two-way analysis of variance, and we are using that to analyze the completely randomized block design. The completely randomized block design. So please permit me to give us the two-way Anova format for the completely randomized block design. I hope this has been taken, the statistical models for the one-way Anova and for the two-way Anova. Now permit me to go straight to to the two-way Anova format. Two-way Anova format. So we have the two-way analysis of variance format. It's very, very important we have that. So we have the XV, the source of variation. We have the degrees of freedom. We have the sum of squares. We have the mean sum of squares, and we have the F ratio. This F ratio is also called the Fisher ratio. Fisher is known as the Fisher ratio. So F is the short form for Fisher. You know, the analysis of variance was designed by Sir Ronald Fisher, an English statistician. So his name, this F means Fisher. It's called the Fisher ratio. So it's the short form of Fisher is F. So this was designed by Sir Ronald Fisher. Now let us go and see how we can have this. So the first source of variation here is treatment. And the treatment has the degree of freedom to be K minus 1. And the sum of square for the treatment is SST. Then the mean sum of square for the treatment is MST, mean sum of square for treatment, and that is equal to SST over K minus 1. Then the F ratio will now be there. Then the second source of variation is the block. And this one is R minus 1. So we have the XXB, sum of squares for the block. Then we have the mean sum of square for the block, and that is equal to sum of square for the block all over R minus 1, all over the corresponding degrees of freedom. Then of course, our next one, of course, is the error term. The error is, you always create room for the error. You always create room for the error. So the error term is only, if you take a look at the model for the statistical model for the two-way analysis of variance and the one-way analysis of variance, that is, you see the error term is always there. So the error term, so the degrees of freedom for the error is K minus 1 into R minus 1. So, and the sum of square for it is XX error, sum of square for error. Then of course, this leads us to the total. So we have the total. There's also a column for the total. So for the total, the degrees of freedom is RK minus 1. Then the SS total is known as the total sum of square, so that we can differentiate it from the sum of square for treatment. So this is TSS. We use the TSS to represent the total sum of square. Total sum of square. This one is sum of square for treatment, so that we can differentiate it. Then the mean sum of square for error is mean sum of square for error, and that is equal to the sum of square for error all over the degrees of freedom. That will be K minus 1 into R minus 1. So that is what you are going to have. So you use the corresponding degrees of freedom to divide the sum of squares. Then at the end of the day, you will get the mean sum of squares. You have that. So now, the F ratio, we are going to have two F ratios. One will be for the treatment. So for the treatment, the F ratio for the treatment, this will now be the M, the mean sum of square for treatment, all over the mean sum of square for error. Then the one for the block will be the mean sum of square for block, all over the mean sum of square for error. So you use error, so that's how you now get. So you are going to have, it's like you conducting two tests in one. It's like you are conducting two tests in one. Of course, here our K means the number of treatments. Then our arrow means the number of blocks. That is what our K means. That's what our arrow means. So we are going to be getting, of course, before we start our calculation, we are going to calculate there are formula for calculating the sum of square for treatment, sum of square for block, sum of square, total sum of square, and so on and so forth. So now, permit me to write that out. We'll first of all get our correction factor. Our correction factor CF, our correction factor is what will be calculated. Our correction factor is summation y square all over RK. Then our sum of square for treatment, this one will now be giving us summation y square I all over summation y square I all over R, or just put it all over R minus the correction factor. Then our sum of square for block will be equal to summation y square j all over k minus the correction factor. That is sum of square. Then the total sum of square is total sum of square. That will be equal to summation. It will be summation y square minus the correction factor. That's what our the total sum of square is. That's the TXX. So this one will be the IJ. Of course, I running from 1 to K. Then the other one, I is equals to 1 to K. J is equal to 1 to R. So we have the number of treatment is K, while the number of blocks is R. So of course, you will know that our TSS, total sum of square, is equal to sum of square for treatment plus sum of square for block plus sum of square for error. So when we want to get that of error, we subtract sum of square for treatment and sum of square from block from the total sum of square to get the sum of square for error. It is as simple as that. So this is the Anova design for the two-way analysis of variance. This is the two-way analysis of variance format, and the essence of this is to make the essence of adding the block, because each block contains all the treatment, is to make the experiment more efficient. If the blocks are not there, you will see that if it were to be the one-way Anova, this source of variation, the block will not be there. So the error will claim the total number of will claim a higher number of degrees of freedom. But now that the block is there, the number of degrees of freedom for the error is reduced because of the block. So it makes the experiment more efficient. It makes it more reliable. So it makes the result better than the one-way test. There is a test that is called the reliability test. We use the reliability test to test for efficiency between these two designs, the completely randomized design and the completely randomized block design. The difference is the addition of the block. If the block is removed, it is the same as the one-way Anova for analyzing the completely randomized design. The samples are taken, they are drawn randomly, and they are independent. So each sample is expected to be drawn from a continuous population, or from a population that is assumed to be normally distributed. So the factor, this one is also a two-factor analysis of variance. The two factors are categorical, but their responses are numerical. So that makes it also a parametric test. So now this is the Anova design for the two analysis of variance or the completely randomized block design. Now we are going to pick solve a particular problem. In statistics, we don't just or mathematics, the best way to explain how a method works is by solving a particular problem. I believe you have taken note of this Anova format. This format, we are going to be applying it. We are going to be using it the way it is when we pick up an example to solve a real life problem to analyze using the two-way. So you will know why it's a two-way, because two factors that are categorical are involved. And what makes it a parametric test is that these two factors are their responses are numerical. So permit me now to go straight to the example. 5 mechanical engineers. We can use it in engineering, in agriculture, in building. So 5 mechanical engineers. 5 mechanical engineers score 4 products. Score 4 products from score 4 products from a mechanical engineering company. From a mechanical engineering company. So, for a mechanical engineering company, okay, on a 10-point scale, on a 10-point scale. Now, the question is, test, the result is given in the table below, but the question is test at 5%, test at alpha is equal to 5% for significance difference among the products and the judgments by the mechanical engineers. So the test should be carried out at 5%. Now we are going to write them out. We are going to see the products. The products are the treatments. Then we have the mech engineers. The products are A, B, C, D. There are 4 products, A, B, C, and D. And the engineers are 5. 1, 2, 3, 4, and 5. So permit me to roll it this way. So for the first one, you have 7, 9, 8, 7, 9, 8, 7, 8. Then the second one is 10, 10, 8, 10, 10, 8, 8, 9. Then the third one is 7, 5546. Then the fourth one from the last product or the treatment is 7, 4, and 4. Now it is very important you create columns and rows for the totals. So when you create this, you are going to have a very good result. So permit us to go now. So the totals from this is 39. Then the total from the other one for B is 45. Then you have to bring out your calculator as you are learning. Then the total for the next one is 27. Then the total for the last one is 29. So this is 45. This is 39. Then the sum for the rows, the first one is 32. The next one is 39 plus 10 plus 5 plus 6 is 30. The next one is 28. Then the next one is 23. Then the last one, 8 plus 9 plus 6 plus 4. The last one is 27. Then the grand total, you add this and you add this, you will get a sum of 140. So our grand total is 140. Now you can see that the problem says we should test for significant difference among the products and among the judgments made by the mechanical engineers. This leads us to the solution, step 1. So step 1 involves the hypothesis. Step 1. State HO and H1. Now, beloved, this is a two-way analysis of variance. The products are the treatments, the judgments by the engineers are the blocks. So you can put it in bracket blocks. So the judgments are the blocks. So this means because it is a two-way analysis of variance, we are going to have two sets of hypotheses. So we'll now see for treatment, our HO will be no significance difference among the products. Then our H1 will be, you know, the H1 is always contradicting the HO. So the H1 will say there is significance difference among the products. So you can see that. Then we are going to set the hypothesis for the blocks. So for blocks HO, there is no significance difference in the judgment by the mech engineers. Then our H1 will be there is significance difference in the judgment. That means the judgments are different, but the HO for the blocks, I'm talking about the various judgments by the 5 engineers. The HO will say there is no signal difference in the judgment done by the 5 engineers, while the alternative hypothesis will say there is a significant difference in the judgment made by the 5 engineers. That is step 1. So step 1, you are to carry out, or you are to state the hypothesis. Please permit me to clean this particular question so that we can have enough space to continue with what we are doing. So we have stated the null and alternative hypothesis. So the null hypothesis will always tell you that there is no significant difference. They are the same. That's why if it's for the means, it will tell you that the population means are the same. The mean of the first population is equal to the mean of the second population, is equal to the mean of the third population. That is, the population means are equal using variances to test for that. Then the alternative hypothesis will tell you that no, the means are not the same. At least 2 population means are not the same. So the null hypothesis is there. It is the hypothesis that is assumed to be true until it is tested. I told you during our test of hypothesis, a thesis is a statement or something that has been tested to be true. That is what a thesis is. While a hypothesis is something or a statement that is yet to be tested to be true or correct. So the null hypothesis is the hypothesis that is under the assumption that it is true. While the alternative hypothesis will always contradict or oppose or negate the null hypothesis. Now this takes us to step 2. Step 2, we have to compute the sum of squares. The sum of squares. So now the first thing we are calculating here is what we call, for this particular problem, note the number of treatment is K. So here our K, let's bring out the ingredients. Our K is 1, 2, 3, 4. Our K is 4. Then the number of blocks are the number of engineers that made the judgment, which is R. R is equal to 5. So R is equal to 5. That is what R is. So now the first thing is to calculate our correction factor. And our correction factor is summation y square all over KR. Now this y is talking about the grand total. So this will be 140 square all over our k is 4 times 5. So that will be 140 square over that. You are going to have 980. So our correction factor is 980. So of course you square 40 and divide it by 20, because 4 times 5 is 20. That is what you are going to do. So that is the correction factor. So now the next one is to go for the sum of square for treatments. Sum of squares for treatments. So the correction factor is the grand total square all over the total. If you look at it, the total number of observation is 20. 4 by 5 is 20. So that is, we have 4 treatments, 5 blocks. So, and if you count each of them, is 20. So that's why you are dividing the grand total square all over the total number of observation, which is 20, which is 4 by 5. So when we talk about the 2-factor or the 2-way analysis of variance, one factor will be on the column, the other factor will be on the row. It's either the block is on the row or the column, or the treatment is on the row on the column. So that makes it the 2-factor, forming a form of matrix. So that is the way it works. So now permit me to clean the step 1, the hypothesis set. I hope you have taken note of the hypothesis. So we are going to look at the next thing we want to calculate. We want to first of all get the total sum of square. The total sum of square is TSS, and that is equal to summation y square ij all over, okay, there's no all over, minus CF, and that will be equal to, that means you are going to take the square of each of these, the square of each of that minus the correction factor. So that's why it runs from the row to the column, from I equal to 1 to k, and j is equal to 1 to r. So you start from here, 7 square plus 9 square plus 8 square plus 7 square plus 8 square plus 10 square plus 10 square plus 8 square plus 8 square plus 9 square, we come here again, plus 7 square plus 5 square plus 5 square plus 4 square plus 6 square, we come here again, plus 8 square plus 6 square plus 7 square plus 4 square, and the last one plus 4 square. You cover the bracket, then minus our CF is 980. So you can see, even if they are hundreds, yeah, but we have statistical packages that can run this. We can use the SPSS, we can use the eView. There are many statistical packages that can run all this. But if you don't know how it is done manually, even you won't be able to know how to run it using any of the statistical softwares. And even if the results, you get the results from the statistical software, you will not be able to interpret them. So that's why it is very important to have that. So you can see now that it runs, if you count, the 20 must be there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You ensure that no one is omitted. There are no omission. And each of them is squared. You square before summing. Each of them, you square each of them before taking the sum. So our total sum of square, which is our TSS, if you now take the sum of all that, you are going to have 1048. It will be 1048 minus 980. 1048 minus 980. So it's equal to 1040. So our TSX, when you carry out that subtraction, our TSS will be 68. You can put it in 2 decimal places. Now the sum of square for treatment is given as summation yi square all over r minus the correction factor. That is what the sum of square for treatment is, and it's SST. So this is how it goes. So it's going to be our SST will now be equal to, you open the bracket, now look at the sum of the treatments. The sum of treatment A is 39. So and that it has, that's why you can see we are dividing by arrow. Arrow is the number of blocks. Each of them has 4. Each treatment has 4 entries. 1, 2, 3. So that's 5 entries. Sorry. 1, 2, 3, 4, 5. That's why we are dividing by 5, which is arrow, the number of blocks. So this will be, the first one is 39 square all over 5, plus you have to square it from, that's what the formula says. The next one is plus 45 square all over 5 plus 27 square all over 5, then plus 29 square all over 5, then you cover the bracelet, minus our CF is 980. So our sum of square for total, for treatments rather, when you carry out that arithmetic, you square 39 before you divide it by 5, square 45 divided by 5, and you now take the sum of that. You are going to have 1023.2. 1023.2 minus 980, and that will now give us 43.2. 43.2. So our sum of squares for treatment will now be it will now be 43.2. So we have gotten that. So now we want to get our sum of square for blocks. Sum of square for block. So our XXB, permit me to write it here. Permit me to clean this part. Is step 2, so that we can get our sum of square for block. So our sum of square for block, that we can get it. Now, our sum of square for block will be equal to summation yj square all over k minus cf, and that will be equal to, look at it here. Now, what are the blocks? The blocks are the judgments given by the mechanical engineers, and their totals are here. So when you talk about summation, we are talking about the totals. The same way we talk about the summation for the treatment, we talk about the total for the treatment. And now you can see that each block has 4 entries. Each block has the whole, that's what we said by definition. Each block contains all the treatments. Block 1 has the 4 treatments. Block 2 has the 4. So the first mechanical engineer judged the 4 products. The second mechanical engineer judged the 4 products on a scale of 10. You can see no score here is more than 10. They judge the product based on their quality on a scale of 10. So each mechanical engineer, which is the block, has the 4 treatments. So now this will now be the first total here. You open the bracket, it will be 32 square all over 4. 1, 2, 3, 4. So plus the next one is 30 square all over 4. Plus the next one is 28 square all over 4. The next one is 23 square all over 4. Plus the next one, 27 square all over 4. You cover the bracket minus 980. You see that? Minus 980. So we are putting the sum of the total sum of square. So permit me to clean this part also, so that we can have enough space to write. Permit me to clean this part also. So the sum of square for treatment is still there. So now, if you have that, what you need to do is to get the sum where you square 32 divided by 4, you write them out, and you now add it. You are going to have the sum of this part is going to be 991.5 minus 980, and that is going to give us 11.5. So our sum of square for blocks is 11.5. Now remember, our total sum of square TSS is the same thing as the sum of square for treatment plus the sum of square for block plus the sum of square for error. Sum of square for error. So our sum of square for error, SSE, will now be equal to the total sum of square minus the sum of square for treatment minus sum of square for block. So our SSE, so our sum of square, total sum of square is 68, remember? Is 68 minus sum of square for treatment 43.2, then our sum of square for block minus 11.5. So our sum of square for error will be 13.3. You carry out this simple arithmetic. So we have been able to get all the sums of squares. We have been able to get all the sums of squares. So the third stage now, or the third step, is to construct the two-way analysis of variance table. construct a two-way analysis of variance table. I hope you have taken note of this value. The sum of square for treatment is 4.3.2. The sum of square for block is 11.5. The sum of square for error is 13.3. Then the total sum of square, which is the TSS, is 68. So permit me to rub everything up so that we go straight to step 3. We are gradually coming to the end of this problem. Beloved, my name is Dr. Crbd. I'm teaching the two-way analysis of variance, or you can call it the completely randomized block design. We use the two-way analysis of variance to analyze that. And if you find this video interesting, please share them in your social media platform, your Facebook, your WhatsApp, and other social media platform. And click on my subscribe to my YouTube channel, Dr. Crbd. Share my videos. Click on the like button. Click on the bell button, so that anytime I upload a video, you will have a notification. Please wait patiently, as it will be very interesting to see whether the HO is accepted or rejected for each of the set of hypotheses. Now, step 3. Construct the two-way Anova table. That is what we want to construct. Now we will go. We have our XV, source of variation. We have our DF, degrees of freedom. We have our SS, these are not new to you. We have our MSS, mean sum of square. And we have our F ratio, the Fisher ratio. That is what we use to decide. So permit me to rule it out. Then our first source of variation is treatment, which is the product. You can call it product. Then you put it in bracket treatment. You put it in bracket treatments. So then the degrees of freedom again is K minus 1, and our K, we have 4 treatments, A, B, C, and D. So our K, this will be 4 minus 1 is equal to 3. Then the sum of square for treatment, XX treatment, is 43.2. So SST is equal to 43.2. Then, of course, the main sum of square for treatment, so MST is equal to, we are dividing it by the corresponding degrees of freedom. So our MST will be 43.2 all over 3. So our MST, that is mean sum of square for treatment, it will be 14.4. 14.4. So our next source of variation is the MEG engineers, which are the blocks. So our degrees of freedom for that is R minus 1, and the number of R is 5 minus 1, and that is equal to 4. So we have 5 engineers, so that is equal to 4. Then the sum of square for block is 11.5. So our, permit me to rule it. So our SSB is equal to 11.5. Then our main sum of square for block, MXB, is equal to 11.5 all over 4. And that will give us 11.5 divided by 4. That will give us 2.875. 2.875. So So we come down here again. Then we have for the error, there is always an error term. So error term is k minus 1 into r minus 1. K minus 1, that is the 4 minus 1 is 3 times 5 minus 1 is 4, that is 12. So our SS error is equal to 13.3. It was calculated. Then now, permit me to roll a line. Yeah, okay, let me bring this down a little. Let me bring it down a little. So our SSE is equal to 13.3. So for error you have k minus 1 into r minus 1. So this will be 3 times 4 is equal to 12. That's what you have there. So for the main sum of square for error, so if I meant to roll this line, the main sum of square for error, is equal to 13.3 all over the corresponding degrees of freedom, 12. That will be equal to 1.10833. 1.10833. That's what you have. So the next one that we have is for the total. So we have for total. So remember our total is RK minus 1, which is equal to RK is 20 minus 1, and that is 19. So if you come here now, and you sum the degrees of freedom, 3 plus 4 is 7, 7 plus 12 is 19. So we have 19 here, which is also correct. That is the sum, the total of the degrees of freedom. So you have that. Then of course the total sum of square, which is our TSS, is equal to 68.00. If you had 43.2 plus 11.5 plus 13.3, you will have that. So now that we have that, it is good. We now go and get our F ratio, because the test is two-way. So we are going to have two F ratios. The first F ratio, because we have two hypotheses to test, two sets of hypotheses. The first set is for treatment. The treatments are the product. There's no significant difference among the products. That's what HO says. The H1 says there's significant difference among the product. Then the second set of hypotheses is for the blocks, talking about the judgment by the mechanical engineers. The judgment, the HO says there's no significant difference in the judgment by the 5 mechanical engineers. Then the alternative is saying there is significant difference in the judgment. The judgments are not the same. So let's see what we have here now. So for treatment, permit me to still share. For treatment, F ratio for treatment will be the value that we have here. It will be 14.4 all over the main sum of square for error. That's what we use. So that's what we, let me write it again. It will be MS treatment all over MSE, and that is equal to 14.4 all over 14.4 all over 1.10833, and that will be equal to, if you carry out that division, you are going to have 12.99. So you are going to have 12.99. Then for this one is also MX block, mean sum of square for block, all over mean sum of square for error. You use the error to divide all through. So this will be 2.875 all over 1.10833, and that will give us, when you carry out that arithmetic, you are going to have 2.59. 2.59, that's what you are going to have. So you can see how far we have gone. Now step 4. Step 4 is to get the table values. Step 4, permit me to write it here. Step 4 Step 4 is to get the table values. That is what step 4 says, is to get the table values. So without the table values, it will be impossible to conclude. So step 4, get the table values. And this is how we are going to get. We are going to get for treatment and we are going to get for blocks. Now for treatment, this is what we are going to have. What's the degree of freedom for treatment? We are going to have F, our alpha is 0.05. Then the degrees of freedom for treatment is 3. Then the degrees of freedom for error is 12. So we make use of degree of freedom for error. You check 3 under 12. You are going to add 5% on the F table. You are going to have 3.49. All you just need to do, then for the blocks, our F for the table value will be 0.05, what is the degree of freedom for the block is 4. You still make use of the degrees of freedom for error, which is 12. So you're going to check 4 under 12 and you're going to have 3.26. So you have 3.26. So these are the 2 table values that we are going to use. So step 5, you are going to decide and make a conclusion. So step 5, you are going to decide and conclude. Now for treatment, look at the decision we are going to make. Now we say that if the calculated value is greater than the table value, we reject HO. So the judgment for treatment is that what is the calculated value for treatment? Beloved, you can see that we have been able to get the table values for treatment and for blocks. The table value for treatment, the test is carried out at alpha equals 5%. So the degrees of freedom for treatment is 3. Then it's against that of the error. So the degree of freedom for error is 12. So you check 3 under 12 and you will get the value of 3.49. Then also for blocks, we use the degrees of freedom for blocks as against that of degrees of freedom of error. So at 5%, that is 0.05. You check 4 under 12. You now get 3.26. This now takes us to step 5. Beloved, step 5 has to do with our decision and conclusion. Now, if you look at the F ratio for treatment, the F ratio that is calculated F for treatment is 12.99, and the table value for treatment is 3.49. And the decision rule states, we said that from the beginning, even in our test of hypothesis, if the calculated value is greater than the table value, you reject the null hypothesis. But if the calculated value is less than the table value, you accept the null hypothesis. Both hypotheses cannot be accepted and rejected at the same time. When you accept one, you reject the other. So now our calculated F for treatment is 12.99, and it is greater than our table F of 3.49. So for treatment, we reject HO, the null hypothesis HO. And what does HO say? HO says, HO, which is the null hypothesis, says that there is no significant difference among the 4 products. So by so doing, we are going to reject HO and accept H1. H1 says there is significant difference among the products. That is the decision and the conclusion for treatment. Then for the blocks, you will see there, the calculated F for block is 2.59. Then the table value for block is 3.26. So this simply means that the calculated value for block is less than the table value. So if calculated value is less than table value, we accept HO, the null hypothesis. And when we are accepting HO, the null hypothesis, we are rejecting H1, the alternative hypothesis. We are now going to accept HO and conclude that there is no significant difference in the judgment made by the 5 mechanical engineers. Beloved, we have come to the end of this class for today. You can see how the two-way analysis of variance test has been conducted, how we have used the two-way analysis of variance to analyze the completely randomized block design. The completely randomized block design is one of the designs used for the design and analysis of experiment. There are various designs. The one-way Anova analysis of variance is used to analyze the completely randomized design. Then when an additional source of variation, which is the block, is added, we use the two-way design. Now, in our next class, we'll be looking at an additional source of variation again, which is now, we are now going to have 3 sources of variation: the treatment, the row effect, and the column effect. That will now take us to the Latin square design. So in our next class, we'll be looking at the Latin square design. All these designs are under a special topic in statistics, which we call design and analysis of experiments. Design analysis of experiment, and we make use of the analysis of variance, test, and the Anova test by Sir Ronald Fisher, an English statistician. And that is the F ratio is named after him. It's also called the Fisher ratio or the F ratio. The F ratio or the Anova test is used for comparing means, using variances to compare means. And again, for this test, we also know that the mean sum of square for error is the estimated population mean. So our estimated population mean for this particular test we just conducted is the mean sum of square for error. That is that value 1.10833. That is our estimated population mean for this test. I believe you have learned a lot from this topic. Please watch the video from the beginning to the end. Subscribe to my YouTube channel, Dr. Chris Esekaibe. And as you do, click to the share to the notification button so that anytime I upload a video, you will have a notification. Share my videos across your social media platform, like my videos, and as you do, God will bless you. Expect my next video on the Latin square design. God bless you. Enjoy the rest of the day. Bye.